Hello, everybody. Mike Muller here again from Rutgers University. Today, we will focus on motor systems, and it will be broken up into two episodes because there is so much to cover. Throughout this series, we'll be exploring motors and their efficiencies, as well as how to maintain and track motor operations, the issue of rewinding a motor versus replacing it, something about variable speed drives, special applications, and some info on fans and pumps. So why are we focusing on motors? Well, 65% of electricity consumed by industry goes into motors. This converts to about $90 billion per year, while also generating lots of CO2. When we look at the cost of motors, they're relatively cheap. So the cost of electricity for operating the motor turns out to be many times their initial cost. Now today, in addition to the motors themselves, we want to focus on the total motor system because losses in the motor system can really dwarf losses in the motor itself. Slippage in belts, poorly designed systems, having them operate when they're not needed, etc. Now, we interrupt this scheduled broadcast about motors to talk a little bit about electricity. Most of us will have a lot of familiarity with single-phase motors, which for us will be the smaller motors we see. We have 120 volts, 60 hertz cycles coming into our homes, and that'll drive motors that will power fans or whatever else you may need, like charging your computer or turning on a lamp. It's important to understand that the single-phase motor has a sort of wobble in the power that it produces. This plot here is the phase of a 60-cycle rotation over time. So this will be 60 times per second where you'll see a full rotation. The red refers to the voltage reading, and the blue refers to the amps. The green line is the power produced, labeled as VI, remember Ohm's law, which does give you the power. But you can see that a couple times in 360 degrees, you're going to go to zero power output. So it's gone from wherever its maximum was back down to zero twice every 360 degrees, which can lead to a little bit of wobble, and if you have a lot of load on the motor, it can also lead the motor to stall. Now this brings us to the idea of three-phase power and three-phase motors. Three-phase motors are a little more complicated, and often it's the bigger motors in industry use the three-phase power, where the same 60 cycle, which can be any voltage, is going to have three different lines coming in, and each of them will be 120 degrees out of phase with the others. Now, as you can see, we have a red line, yellow line, and blue line, all representing voltage, and all of which are 120 degrees out of phase from each other. If you do the same thing that we did previously, where you determine the power being put out by all three of these lines, you see that the total power is essentially constant. Now, in real life, there's going to be a little ripple. But if you calculate this theoretical output and do the trigonometry, the output power from a three-phase system is constant. Now you can imagine that in an industrial motor situation, having a constant input and output power to the motor is very valuable. And so in some cases, we'll have single-phase motors, but in the substantial majority, we'll see three-phase motors. Okay, back to the motors themselves, and let's talk a little bit about their efficiencies. In the old days, we already knew how to make more efficient motors. But the problem was that although it was simple, it was expensive. In one simple way, the more copper you use in the windings and the less aluminum, the higher the efficiency. But most people just want to buy the cheapest motor possible, so there was very little reason to make motors more efficient at all. And so, prior to some important legislation in 1997 on energy policy, there were very poor motors out there on the market that would run hot and people would still buy them. But after 1997, the law made it so that only energy efficient motors could be made by putting a lower limit on the efficiency. Now you could still buy even better motors, referred to as premium efficient motors, but the increase in price made this not an obvious choice. As you can see from this chart, the motor efficiencies in general are not as bad compared to other systems we look at. They're pretty high. Now, for some of the smaller motors, it can get a little low. For a 1.5 horsepower motor, we're down to an efficiency of about 82%. So you could say there's energy to be saved there. But now you move to larger motors, you can see 94.5%, 95% efficiency, and that's getting pretty darn good. So it's going to be hard to improve on this. However, the question remains, does it make sense to go out and buy that premium efficient motor? So now, as you can see here, there's a 1.5% improvement for a premium 1.5 horsepower motor, but only a 1% improvement for a 10 horsepower motor when you buy the more expensive one. So does it make sense as a smart investment? Here's an example of just that. We can see from a motor catalog of the listing of two motors. The first is a premium efficient motor, and the other is an EPAC motor, one of the minimum efficiency motors by the 1997 Energy Policy Act. For a 10 horsepower motor, the premium motor costs $1,451, while the EPAC costs only $1,212. So that's $239 to get the premium motor, meaning you pay about a 20% premium for the high efficiency motor. Now, if we do a quick calculation with a 10 horsepower motor at 89% efficiency, and that means, by the way, that it'll consume about 11.25 horsepower to get to those 10 horsepower, and estimating that you run it at 80% load for 8,000 hours per year, that's a lot, but we're seeing if we can make our money back. That ends up using about 53,600 kilowatt hours. At about a dime per kilowatt hour, this will cost you about $5,300 per year to operate that motor. Now, if you get a 1% improvement in efficiency, that's going to turn out to save you about $54 per year. And based on the cost difference, it's going to take you about 4.5 years to make your money back. Now, that's not outrageous, but we find that in U.S. industry, that is unlikely to be a payback that will get people to move. And so in general, we find people putting in regular efficiency motors or EPAC motors and not the premium efficiency motors. Now, in terms of premium over EPAC efficiency motors, here's a chart of their types and their efficiencies. You can see that the difference is not great. That's why we do not see premium efficient motors out there very often. Next, let's look at motor inefficiencies. Where do they go bad? Well, we'll know pretty well where these losses come from. The first is resistance heating, the so-called I2R losses. All motors will have some resistance, and you will have to push the electricity through a resistive wire, and that's going to have an I2R loss according to Ohm's law. Now, you're also creating an electrical field within the core, for example, and that electrical field can have currents, which are wasted motion of electrons. We also have stray losses from manufacturing defects, as well as other mechanical losses. Some of these mechanical losses could be friction. And if you say, well, where's the friction? A motor will stop spinning once you take the power off, so the only thing that's going to stop it is friction. And then there's windage loss, which is the fact that you have to cool motors down. In most cases, this means fans are needed, and the fans there to cool the motors, and running those fans takes energy as well. Despite these losses overall, we're finding that the motors themselves are pretty efficient. And so often when we study motor systems, we can always find ways to improve your operations. You can spend extra money for extra efficiency in your motors, or you could improve the flow of motors for cooling, although it's rarely cost effective. You can maintain them better by keeping them from getting in a position where there are those losses or those losses increase. You can also size them correctly, understanding that motors that are sized incorrectly and are operating in a fraction of their design load are going to be less efficient. And finally, the system needs to be efficiently designed. Now let's spend a few minutes talking about motor maintenance. Now, when I write up a recommendation on maintenance, I put everything into a catch-all and say you should begin a motor maintenance program. I do this simply because motors themselves are so efficient that plants often ignore this stuff. And what you really want to talk to plants about is not only the motor efficiency, but also motor failures. We want to reduce the downtime by reducing the failures and thereby reducing repair costs. And this is what usually gets the management's attention, not the energy impacts. As an aside, in the old days, we always talked about lubrication practice when referring to maintenance. But in today's world, most of the bearings associated with motors themselves are sealed at the factory and there's no need to worry about lubrication. Also, one of the things that should be obvious, but is not, is cleaning. We often see motors that get coated with dirt and are not cleaned regularly. That dirt can act as an insulator and cause the motor to run hotter. A hotter running motor is going to degrade lubricants and cause trouble in the motor core and increase the I²R losses. Dirt is not the only kind of insulation we see. In some cases, you'll find sound insulation surrounding the motor because they make noise. However, we find that in most plants, unless it's a very quiet plant, sound insulation is unnecessary and raises the temperature of the motor significantly. Something that may surprise a few people is that motors tend to get sick before they die. And what normally happens is that when a motor gets sick, it starts getting hot. And as it gets hot, the windings in the motors get warmer, the resistance goes up, and so it's going to have more I²R losses, and that's going to cause the windings to heat up more and more, and next thing you know, boom, the motor burns out. Now, the motor burning out is not normally the cause of the failure. It was something else that caused it to start to heat up. Possibly blocked air cooling, a wobble from a motor that is not seated well, or it's not aligned with its application and it's causing an asymmetrical load. Any of these things could cause your motor failure. Now, if you fix those things before it fails, you won't have to replace the motor. To predict this, we strongly recommend that motor temperature and vibration levels be tracked. What you're looking for is trend analysis. Whatever temperature it's at when you first measure, I don't care. If it's at 106 degrees, 110 degrees, it doesn't matter. What we want to see is if the temperature changes. Same with vibration levels. Whatever vibration level it's at when it's first installed and operating happily, we want to keep it there. Trending the vibrations, you can see if the level changes from there. Also, when I'm auditing a plant, as I do my walkthrough, I'll reach out and touch the motors. Now, I do not recommend this for other people because it's a safety issue. But if I touch a motor and my hand bounces off the motor because it's too warm for me to keep my hand on it, I know that's too hot for the motor to operate. I know there's an issue. But if I can touch it and it's warm but not hot to the point where I have to take my hand off, I know that the motor is in decent shape. Here are a couple of vibration sensors that are attached at a couple of points on a motor. One sensor is aligned on the rotation axis, and the other is perpendicular to the rotation axis. These sensors are typically attached magnetically and can come with either flat or rounded mountings. You can put them on a number of different motors, moving them around, and they're very inexpensive. What I recommend is that you take a little piece of paint or a permanent marker and put a circle around where you're taking that measurement so that you always make the temperature and vibration measurements at the same spot. Now, if your device only measures vibration, then I would put another device on there to measure temperature. They're both very valuable. And always make sure that you're operating at normal conditions so that the motor is as loaded as it normally would be. Okay, so in a perfect world, there's no failure of motors. But unfortunately, we don't live in a perfect world, so we often experience motor failures. Now, we strongly suggest that you have a plan in place to respond to motor failure. Are you going to replace the motor, or are you going to rewind the motor? It'd be nice to keep a backup motor for every motor at the plant, but in general, this can be hard to achieve. One strategy that some places are attempting to use is to use the same motor in many of the applications throughout the plant. This way, we need only one backup motor to provide us with fault tolerance for all 10 of those different applications. So inventory control is one of the things that we like to look at. Now, we're also going to spend a little time here talking about the process of rewinding. Now, you have these windings on the motors that create the magnetic fields. These magnetic fields cause the motors to rotate, and when these windings burn out and you want to rewind it, the question is, can you do that in a way that doesn't hurt the efficiency of the motor? The answer is yes. If you take your time and you rewind it by hand, you can come back with a motor with a higher efficiency than the original motor. Turns out that the speed with which you're doing things becomes what's important and is where the problems arise. If you're in a factory and you have an important motor go down, you need it back up as soon as possible. So you go to the rewind shop and you say, do it very quickly. And in order to do this, excessive temperatures are used, which can have several negative consequences. Now, to appreciate one of the consequential problems, we have to talk a little bit about eddy currents. I know I'm not talking to a lot of electrical engineers here, but these windings that we make tend to go around a core, and typically this core is solid. If this core is solid and you're creating an electric field, you're going to find a lot of internal electric fields going around the solid core. So we're not going to use a perfectly solid core. And what you're going to do is make up your core with a bunch of thin laminations to try and keep these eddy currents from forming. Now, these laminations are thin and insulated from each other, and therefore they knock off these large eddy currents, which otherwise would reduce the efficiency of the motor. So when we're redoing the windings, we have to get the old windings off, and that's called stripping. And we have to strip the old windings off, and generally we use heat to do that. Well, if we use excessive temperature, we can create problems with those laminations in the core, and thus we end up having more eddy current problems in the core. So the typical rule of thumb in the rewind process is you should never go above 750 degrees Fahrenheit. But guess what? To speed up the process, a lot of these burn-off ovens operate up to 1400 degrees Fahrenheit. And that causes the insulation between the laminates to be compromised, which then reduces the efficiency of the motors. And now we go and we do the new windings. And with the windings, we need to use coated wires since we can't have electricity going across the windings. So we put coating on to prevent electrons from going across. But again, we have to cure the winding and get that liquid coating to cure. And if we use too high of a temperature, we can create weak spots in the coating on the windings, which again can lead to a reduction in efficiency. It's a bit of a domino effect. So basically, we end up with a conclusion most of the time when you rewind, you're going to see a 1 to 2% reduction in efficiency. Well, that may be necessary because your plant has to get up and running. So the real trick here is to never rewind a motor more than once. I recommend that once a motor has been rewind, to take a magic marker and put RW in big letters on the motor, which tells you that it's been rewound. And this tells you that you should have a replacement motor available, and that will reduce your downtime. Now, this is going to pay off. And although not many people do it, it's always a very good recommendation to make. Okay, this brings us to the end of our first episode on motor systems. In our next episode, we'll discuss proper motor sizing, VFD applications, only an introduction to that. We're going to have an entire episode on VFDs, and further motor efficiency improvements. Thanks for joining us. Hope to see you again on our next episode of IAC 101.